Good morning, students. So last time we have done the continuous time Markov chain. So today we are going to start with the some application in queuing theory. Okay. So let us say some customers are coming to a bank and they are coming according to some, let us say, process. That process may be Poisson process. That means interarrival times is exponential. And then let us say one server is there, one clerk is there, then customers are coming, they are getting served, and then they leave the system. That is the queuing system. Similarly, you may suppose that instead of clerk we have servers, and instead of customers we have some programs to be queued, and they are processed in the server and then they leave the system. So this kind of system is basically queuing systems. Okay, so I think my screen is visible now. Queuing system. So we have some customers are coming. Okay, so they are coming to, let us say, bank. Then there are some servers, that means there are some clerks are there. Then after that, once service is done, they leave the system. Okay, similarly, some programs are coming, they are processed in the server and then they leave the system. So it may depends on how many servers are there. It may be that there is one server or one clerk is there, or two clerks are there and two servers are there. Okay, so if the arrival pattern is Poisson process, that means the inter-arrival times between the customers is exponential, then that we already know that is denoted by M. And then at the bank, they are getting service according to exponential distribution with the rate mu. Then second M, there may be one clerk. Similarly, other kinds of system are also there. M, M, C. There are C servers or C clerks are there. Okay. Similarly, other kinds of system also there. The first time denotes that the inter-arrival times are exponential. Second time denotes that service time distribution is exponential, and one denote that one server. So these are, so what are the basically random variable involved here? NT is the number of customers in the queuing system at time t. NQT is the number of customer in queue in the queuing system at time t. NST is the number of customer receiving service at time t. So therefore, NT is equal to NQT plus NST, because total number of customer in queuing system is the number of customer which are in queue plus number of customer which are getting service. So we may have steady state solution. That means the solution does not, at t goes to infinity, then steady state solution may exist. So then let us assume that n is the steady state, in steady state number of customers in the system that means in the long time the server this system is working, then in the steady state number of customer in the queuing system. NQ is the steady state number of customer in queue. NS is the steady state number of customer receiving service in the queuing system. So clearly number of customer in the system is same as that of number of customer in queue plus number of customer receiving service. So because these are random variables, so we can take expectation, expected value of n is expected value of nq plus expected value of ns. So expected value of n is the expected number of customer in the queuing system. So that is we can denote by L. This is LQ plus LS. LQ is the expected value of NQ. That means expected number of customer in the queue in the queuing system in steady state. LS is the expected number of customer receiving service. Okay, so let us say what is the relationship between time. So let us denote by random variable small w as the total time a customer spends in the queuing system. Q is the small q is the time spent by the customer in queue. Small s is the time spent in receiving service. In the queuing system. So can anyone tell what is the relationship between W, Q and S? Total time spent. Yeah. Yes. Somebody is saying something?
W equal to Q.
Yeah. W is equal to Q plus S. So clearly, because total time spent is time spent by customer in Q plus time spent in receiving service. So we can take expectation of this because these are random variables. So expected value of W is expected value of Q plus expected value of S. So we are denoting this by capital W, capital Q, WQ, W, S. So W is the expected time or average time spent by the customer in the queuing system. WQ is the expected value of Q, which is the average time spent by the customer in Q. WS is the expected value of S, which is the average time spent by the customer in receiving service. So average service time. Also, we can denote the distribution functions, CDF, WT as probability, small w less than t. That means this is the CDF of small w, WQ T is probability, Q is less than equal to T, WST is the probability, S is less than T. That means this is the CDF of random variable S. Okay, so these are the CDFs basically. Now we know that from a source customers are coming, then customers are coming. So we can say that inter-arrival time which we can denote as tau 1, tau 2, so on, may be independently and identically distributed random variables. For example, if tau i's are independent, IID exponential with parameter lambda, with rate lambda, then we know that if inter-arrival times are independent exponential, then the arrival pattern, that is arrival pattern is Poisson arrival pattern. So okay, so this is the inter-arrival time. So this may be IID random variables. In particular case, they may be IID exponential. That means the arrival pattern is Poisson. After that, they come to the server 1, then server C. Okay, so some servers are there, server N, let us say. Okay, so then they go to the servers. So N is the number of customer in the queuing system. NQ is the number of customer in queue, and NS is the number of customer getting service, and W is the time spent by the customer in the queuing system. Q is the time spent in the queue. S is the time getting the service. So service time distribution may be independently exponential. So that means service time distribution may be independent exponential. That means W ST, that is the CDF is 1 minus e raised to power minus mu t. Okay, if all the servers Ti is the, let us say, time spent by the server, spent by the time spent by the server I for completing service. Okay, so that may be exponential. Okay, so that means Ti is the maybe that Ti time spent by the server I for completing service may be exponential with parameter mu. I is from 1 to n, because we may assume that they are having exponential distribution. Then if there are n persons, then then n servers are busy. Time until next service completion. So because n, we are assuming that n servers are busy, then let us denote the t time until the next service completion. Then t is nothing but minimum of t1, t2, tn. So this may be clearly exponential with parameter n mu. As already we have done this kind of analysis, that minimum is basically exponential n mu. Then what are the notation? Notation is A, B, and C. A is basically denoting the inter-arrival time distribution. B denoting the service time distribution. And C denotes the number of servers. And capital K denotes the system capacity. If it is not specified, then this is basically infinity. Okay. Then AB can be GI, general independent inter-arrival time. G as the general service time. M is the exponential inter-arrival or service time distribution. U is the uniform inter-arrival or service time distribution. D is the deterministic. Inter-arrival or service time distribution. So, for example, if we write MM1 means the inter-arrival times exponential, and second time denotes that service time distribution is exponential. One denotes that one server is there and infinite capacity is there. So this is the notation. Now let us see the basic cost identity. So imagine that the entering customer are forced to pay money according to some rule to the system. system. So then the average rate at which the system earns so this is proportional to the average amount the average arrival rate of the customer into average amount and entering customer pays. So where lambda is the average arrival rate of entering customer. So average rate at which system earns is the proportional to the average amount of an entering customer pays. And lambda is basically average arrival rate of the entering customer. So lambda A, we can find out if NT is the number of customers arrival by time t, then lambda A is limit t goes to infinity and t by t. This is the rate of renewal process. So this we will do when we do the renewal process, renewal theory, then we will do this proof also. Lambda is limit as t goes to infinity and t by t. So now from here, let us say what is the relationship between this L and W, LQ and WQ, what are the relationship? So this is the average number of customer in the queuing system. So this is the L is the average number of customer in the queuing system. This is equal to lambda A, average arrival rate, into average amount an entering customer pays. What customer pays here is the time. So this is W, because W is the average time spent by the customer in the queuing system. So average number, what system earns is the customers. So L is the average number of customer in the queuing system is lambda A, and W is the what customer pays. Customer pays its time, average amount the customer spend in the queuing system. In the similar fashion, you can write down LQ is lambda A WQ, LS is lambda A WS. So this is known as the Little's law. So any question till now? Okay, am I audible?
Yes, sir.
Okay. So till now we have done the Little's law. So these are the relationship between various parameters of the queuing system. So let us see what are the solution in birth and death process. Just so we have in the birth and death process, birth rate is lambda n is 0, 1, 2, and so on. Mu n is mu, n is 1, 2, so on. So 0 customer, 1 customer, 2 customer, n minus 1 customer, n customer, so on. So uh, let us say this is yeah, birth rate is lambda n and death rate is mu n. So this is lambda naught, lambda 1, lambda n minus 1, mu 1, mu 2, mu n, and we know that steady state solution exists if S, which is 1 plus C1 plus C2 plus so on, is finite, then steady state solution exists. If and only if S is less, S is finite. Also we know that Cn is lambda naught, lambda 1, lambda n minus 1, mu 1, mu 2, mu n, and P naught is 1 by S, and Pn is probability, n is equal to n, which is Cn P naught, n is 1, 2, and 3, so on. So this is the birth and death process. Now, let us start with a particular case of MM1 queuing system. So that means inter-arrival times are exponential. That means the random arrival pattern. So if there are, let us say, n customer in the queuing system, okay, n is equal to n, and probability of an arrival in interval of length h is, because this is Poisson process, arrival pattern is Poisson. Okay, arrival pattern is Poisson. That means the inter-arrival times are exponential. That means this will be, if there are n customer in the queuing system, e raised to power minus lambda h 1 divided by 1 factorial, because one customer arrival. So this will be lambda h 1 minus lambda h plus lambda h square divided by 2 factorial plus so on. That means this is lambda h plus something of order small o h. So therefore, lambda n is lambda, because we know that inter-arrival times are exponential and service time is exponential. So therefore, this is a birth and death process. And the service time distribution, WST, this is probability S less than T. This is 1 minus e raised to power minus mu T. T is greater than equal to 0. So if customer is receiving service, probability that service completion that means death in interval of short duration, in a short interval h. In the same fashion, this is mu h plus small o h. because that also you can write down from here also, probability that service will be completed in a very small interval. That means 1 minus e raised to power minus mu h. Again, e raised to power minus mu h, you can write down mu h. 1 minus mu h can be written as mu h plus something of order small h. Is it okay? Because 1 e raised to power minus mu h will be 1 minus mu h plus mu h squared divided by 2 factorial and so on. So that 1 and 1 will cancel out. We have mu h plus something of order small h. So you can say that mu n is mu here, n is 1, 2, 3 and so on, n is 0, 1, 2 and so on. So therefore it is clearly a birth and death process with lambda is lambda, mu n is mu. So 0, 1, stationary state diagram is lambda, 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 mu, mu, mu. So let we denote by lambda by mu by rho. Arrival departure ratio. So what is Cn? Lambda, lambda, lambda upon mu, mu, mu. That means lambda by mu raised to power n. That means rho raised to power n. S is 1 plus C1 plus C2 plus so on. That means this is 1 plus rho square plus so on. This is 1 divided by 1 minus rho. So P naught, which is 1 by S, is 1 minus rho. So we know that rho should be less than 1. Then if rho is less than 1, steady state solution does exist. So what is Pn? This is probability. N is equal to n. This is Cn. P naught. Cn is rho raised to power n. One minus rho. N is 0, 1, 2 and so on. So what is the distribution of n here? Rho raised to power n, 1 minus rho, n is 0, 1, 2, 3 and so on. Which distribution is this? What is the distribution of n? Q raised to power n p. Which distribution is this? Geometric, yes. Yeah. So this is geometric distribution. With probability of success as 1 minus rho. So clearly then, because each customer is allowed in the system, okay, because infinite capacity is there, mm1 infinity, that means infinite capacity is there, so each customer is allowed, so average arrival rate is lambda, okay, into probability of with which customers are allowed in the system, that will be probability 1, lambda into 1. So lambda is average arrival rate is lambda. So L is the expected value of n. By geometric distribution, we know that this is Q by P. This is Q by P. So Q here is rho upon 1 minus rho. Also sigma n square variance is Q by P square. Okay, so L is this. So WS is the expected value of S. But service time distribution is, we know that is exponential with parameter mu. That means mean is 1 by mu. And also we know that lambda rho is equal to lambda by mu. So this can be written as rho by lambda also. By Little's law, W is equal to L by lambda A. Lambda A is lambda, because we know that L is equal to lambda A W. Lambda A is lambda. W is equal to L by lambda. So, but this is L by lambda. So rho upon lambda 1 minus rho. So lambda by mu. So this can be written as 1 by mu, 1 minus rho, because rho is lambda by mu. 1 by mu is WS. WS 1 minus rho. So this can be written like this also. And WQ, because we know that WQ is expected value of Q. We know that W is equal to WQ plus WS. So this is W minus WS. So from here, this is 1 divided by 1 minus rho minus 1 WS. So this is rho upon 1 minus rho WS. So in this fashion, we can determine WQ also. Also, LQ, which is expected value of NQ, is lambda WQ by the Little's law. So therefore, this is rho lambda upon 1 minus rho WS. Just plugging in the value here, lambda WQ value we are plugging from here. So now, now we know that lambda WS yeah, from here lambda WS is rho. So this is rho square upon 1 minus rho, because rho is equal to lambda WS star 1. So this is rho square upon 1 minus rho. So these are the values we have already calculated. Now L cube. From there we have determined the LS also. So WS is with us, W is with us, WQ is with us. Also we know that L is equal to LQ plus LS. Okay, so what is the probability that server is busy? So this is the probability that 1 minus probability that, because only one server is there. So this is 1 minus probability that server is empty. Server is empty when no customer is there. So 1 minus probability n is equal to 0. N is equal to 0 is 1 minus rho. So therefore this is 1 minus rho. This is rho. Which rho is, we know that is lambda ws also. This is known as the server utilization. Probability that server is busy is server utilization. Okay. That means fraction of time. Server is busy. And rho is lambda by s. This is the arrival service ratio, lambda by mu. And performance of the queuing system is determined by W, WQ, L, LQ, LS, WS, as well as PN. Okay, so any question till now? So let us say that, suppose that customer arrive at a Poisson rate 1 per every 12 minutes. And that the service time is exponential at a rate of one service per 8 minutes. Determine the what are the parameter of MM1 queuing system. So we are saying that only one server is there. Only one server is there. So what are the parameters of the queuing system? So because MM1 queuing system, so what is the lambda arrival rate? So customer arrive at a poison rate of 1 per every 12 minutes. So rate is 1 by 12 and mu is the service time is exponential at a rate of 1 service per 8 minutes. So 1 by 8. So what is the arrival service ratio? This is less than 1. So therefore, because rho is less than 1, so therefore the steady state solution exists, or limiting probability exists. Okay. Now, what is L? L is rho upon 1 minus rho. This already we have determined. L. L is the average number of customer in the queuing system is rho upon 1 minus rho. So this is 2 by 3 upon 1 by 3. 2 customer. LQ. LQ already we have determined for MM1. Rho square upon 1 minus rho. So this is 2 by 3 square upon 1 by 3. 4 by 3. And W is L by lambda by Little's law. 2 upon 1 by 12. 24. That means average time spent by the customer in the queuing system is 24 minutes. And WQ is the, either you can determine by rho WS upon 1 minus rho, or you can determine by LQ also. So LQ upon lambda. So this is 4 by 3 into lambda is 12. 16 minute. Okay. So what is WS? Either you determine W minus WQ or 1 by mu 8 minute. What is LS? Anyone? What is LS?
Two by three.
2 by 3 lambda. Either you can determine uh, L minus LQ or lambda WS also you can determine. So this is 8 by 12. 2 by 3. So this is the average number of customer getting service. Okay, so this was about this parameters of the queuing system. So next time we have to determine what are the CDFs of random variable small w, small q, and for small s we know, because small s basically the service time distribution is exponential, so that we know is exponential. Ws we know, w we know in general. For w is exponential, ws, yeah. So that means s is exponential with parameter with parameter mu, with parameter mu. Okay, so next time we will determine the CDFs basically of all. Okay, let us stop here. So